A superconducting ring has a radius of 1.4 centimeter and mass 30 gram. So this wire has a mass of 30 gram, circular coil has a mass of 30 gram, and it is having a radius of 1.4 centimeters. So it is given here, this black ring carrying current in this direction like this. The ring carries a constant current I and is placed in a 0.5 Tesla magnetic field with field lines that are tilted at an angle of 20 degree outward from the vertical at very location around the ring. So the ring is like this and magnetic field lines are directed like this. They are making an angle of 20 degree with the vertical. That is what is indicated here. So this angle is 20 degrees. Then what amount of current I in ampere must flow through the ring? So they have shown the direction of current. What amount of I must flow through the ring so that the ring will float in the magnetic field. It will float means the net force acting on the ring must be 0. So one is weight of the ring. Weight of the ring will put it down, mg. And they expect the force due to magnetic field, that is force experienced by a current carrying element placed in a magnetic field, and that force due to magnetic field should act vertically upward so that net force is 0. The ring will appear to be floating in air. That's what is expected. So now if you get into the directions of the force, weight will act definitely downwards. The weight of the ring will act at the center of mass, that is the center of the ring. So that will be vertically downwards. Now that means magnetic force due to magnetic field should be vertically upwards. Now if I take a small piece of wire here from this place, or anywhere you can take it. For the timing, I'll take a small part of the wire here in this place. Then I can take it as a conductor carrying current outside the paper like this. So it is carrying current outside. So I have kept a wire like this, which is carrying current out of the paper like this. Okay. And what about the magnetic field? So now the magnetic field can be split into two components. One is along this direction, I can take B cos 20 here, B cos 20, and there is a magnetic field in this direction, component of this, B sin 20. So there is a magnetic field like this way also. Magnetic field is like this, B sin 20. So if you stretch the first three fingers of the left hand, then the middle finger should be coming out of the board because it represents the current direction. So current is represented by middle finger. So put the middle finger out of the board and put the forefinger should be in this direction. The left hand forefinger should be pointing outside like this, towards the right. And the middle finger should be coming out of the screen. Then the thumb represents upward force. This is the direction of the thumb. So you can check it. So by considering the x component of the magnetic field, out of the two magnetic fields, the x component will produce a force which is vertically upwards. So magnetic field is represented by forefinger. So this is the direction of B. And middle finger will represent the direction of current here, vertically outwards from the screen, and then the thumb thumb of the left hand will point upwards. So that is how we can take the magnetic fields. So the this component of the magnetic field will be responsible for the production of force due to magnetic field in the vertically upward direction, which should be balancing the weight. Of course, this component will not, it will produce a force actually. There is a force produced by the y component of magnetic field also, but it will not help us to make the ring to float. So what is the direction of the force due to this component? Let us see. So we have a conductor which is carrying current outside the paper like this. So it is placed like this. It is carrying current outside the paper. Then what about the magnetic field? And if you take the vertical component of magnetic field, it should be like this. So middle finger will be pointing outside because current is like this. And forefinger will be pointing upwards because magnetic field is vertically upwards. I am considering B cos theta now. Then the thumb, which shows the direction, will be showing the direction like this, force. This is represented by thumb. Now what happens is, so this part of the wire will experience a force like this. This part of the wire will experience a force like this. It will simply create a tension in the ring, and the net force will be 0, because for a force here, there is a force here which will cancel. For a force here will cancel. So the net force due to all these components will be 0. That force will not take part in making the ring to float. So we can leave that magnetic field, which is the cos component. That will not be useful for us. So we will take only the x component, that is v sine 20, not x component, v sine 20 component. Okay, so now we have to compare them. So force due to magnetic field should be balanced by force due to gravitational field. Now you know that force due to magnetic field is Q into I into L cross B. I force on a current carrying conductor placed in a magnetic field. I L B sine 9 I L B sine theta. So I L B sine 20 is equal to mg, or I can write simply sine theta. ILB sine 20. So if you substitute for all these things, you will get I is equal to mg divided by ILB sine 20. That implies I is equal to, mass of the ring is given 30 milligram something, 30 gram. So 30 into 10 to the power minus 3 kg, 30 gram. And G is, I will take it as 10 almost. Yes, divided by we have to find out L length. We have to take the 2 pi r instead of it is the full length of the ring, so I can substitute it as 2 pi r. So L can be substituted as 2 pi r. So 2 pi r. Radius of the ring is radius of the ring is 1.4 centimeters. So 1.4 into 10 to the power minus 2. 1.4 into 10 to the power minus 2. 2 pi r is over. B, here I have written one more. This is not, this I is, okay. B, magnetic field strength is 0.5 Tesla, somewhere S, 0.5 Tesla. So L, B, sine 20. Sine 20 is given 0.34. Yes. Now you have to calculate this. The answer of this will be I is equal to almost about 21 amperes. This is the current to be passed. Thank you.